So, hello everyone. Today we are going to start the second lecture of week 5, that is monad equation. So, we will quickly revisit the last lecture. So, there we discussed microbial growth, what is typical growth of microbes, then what are different factors which are affecting the growth rate. In fact, we calculated the specific growth rate and what is generation and doubling time, and finally we discuss some experimental methods, direct and indirect method to measure the microbial growth, like the optical density, dry cell weight. So, in today's lecture we are going to discuss the kinetics of microbial growth. So, as we have seen, either the mass or number changes with the time, then how can we analyze those data, and that whole process is the microbial growth kinetics. In addition, we will be discussing a simple monad equation, how it explains the microbial growth. So, we have already discussed in the last lecture that how microbial reaction is different from the enzymatic reaction. So, in enzymatic reaction, typically enzyme require a substrate. We are having enzyme, this requires a substrate, this forms enzyme substrate complex, then your product is formed. It only requires the substrate, but when you are using living cells, it requires a proper medium. And in addition, the different operational parameter, pH, temperature, dissolved oxygen are required for the growth and product formation. So, this is the major difference between enzymatic and the cellular reactions. And this liquid medium requires following ingredients: carbon source, nitrogen source, minerals and vitamins. So, typically carbon source is required for the cell growth, product formation as an energy source and for the maintenance. Nitrogen source is required for the growth of the cells, and minerals and vitamins mostly work as cofactors in metabolic pathways. Now, we have discussed this also. You can see the growth of cell in two ways. In one case, you can see number of cells per ml. In other case, you can see weight of cells, milligram per ml or per liter. So, typically in the case of unicellular organisms, the mass of living cell is proportional to the number of cells. So, it says M is proportional to N, and then this can be expressed either in terms of number of cells per unit volume or mass per unit volume. But in the case of filamentous organism like mold, the size and density of the cells are not necessarily proportional to their number. So, these are this mass and number is not in proportion. So, the concentration of mold like cells is expressed only in terms of mass per unit volume, not in terms of number. Now, once we are talking the kinetics, so what changes with the time? Cells, there is a cell growth with the time. In addition, the depletion in the nutrients, and there is a formation of products as well. So, we will be seeing the kinetics of cell growth, and separately in the next module we will be seeing the kinetics of substrate utilization and product formation. Now, cell growth, as we have discussed, it can be in the number of cell, that is called population growth, or increase in the size and density. The rate of these processes vary widely as growth occurs. So, it says depending on the cell growth, these two processes, substrate utilization and product formations, are affected. Now, if you see the biochemical processes, so mainly you can have this utilization of material from medium by the cell and generation of metabolic end product in the medium. So, these two processes are also associated with the cell growth. So, what it indicates, there are n number of metabolic reactions are ongoing. Some of them are leading towards the growth of the cell, some of them are leading towards the generation of certain metabolites. Now, how once we put the cells in the medium, there is a certain interaction among environment and biological phase. So, let us say this is a biological phase and this is the environment. Biological phase means cell population, environmental cell, let us say growth medium. Now, what are the interaction among them? It is very interesting to see. The environment, this is still considered as a multi-component. The reaction is taking place in the environment. This acid base equilibria keeps shifting. The variation in the pH, temperature, change in the rheological property like viscosity, and it is a multi-phase system. It is a gas, liquid, liquid or even gas, liquid system. And further we will see there is a spatial non-uniformity in the environmental condition or the growth media. Now, when it comes to the cell population, again it is considered a multi-component system. Each cell is having n number of parallel biochemical reactions, and there is a cell to cell heterogeneity. So, all the cells are not in the same growth phase, and as I told, we are going to have this multi reaction. So, multiple reactions are taking place at the same time. Then there is an internal control which regulate those multiple reactions, and it also impart the adaptability, and finally you will see this entire process is having so much in random that it gives the stochastic environment or stochastic behavior. In addition, there is another challenge, that is the genetic instability. Now, let us see how these two systems interact with each other. First, cell population. What they are going to do? They are going to utilize the nutrient, they are going to utilize the substrate, and the products will be formed and product will be released to the medium. So, nutrients or substrate is travelling from medium to the cell, and product is going from cell to the media. Similar to this, if you see, the cells are generating heat because of their metabolic energetics, and because of generation of this heat there is an increase in the media temperature. So, media temperature is increasing, and this effect of again this temperature is affecting the population of your cell growth. So, again this is a two-way process. Third thing we can discuss, mechanical interactions. It occurs through the pressure and flow of medium to the cell. So, in one case medium is flowing from this, there is a, let us say, mass transfer from environment to the cell, and further cells are generating certain metabolites which can change the rheological property like viscosity, and that is again going to affect this mechanical behavior of the environment or the growth medium. Further, if you just see this, as I told initially, this both pH, temperature, ionic strength and rheological property, it changes with the time, In fact, you just take a simple example of aerated system. In this, gas is dispersed into the liquid. Simple example of gas liquid system. If you are having two hemisphere liquid, that becomes liquid liquid system, and if you are having two hemisphere liquid and gas, then it is gas, liquid and liquid. In addition, we have one more phase, that is the cells. So it's a multi-phase system, and considering the volume of bioreactor, it's not always possible to ensure uniformity or uniform mixing. So it's always expected there may be spatial non-uniformity inside the bioreactor. Now, as I told, in the case of biological system, we consider this a multi-component because parallelly a number of metabolic pathways are ongoing inside the cells, required for their cell growth, required for the product formation, required for the synthesis of any byproduct. Further, all the cells are not in the same phase. Some cells are in the growth phase, some cells are newborn, some cells are in stationary and some may be in the death phase. And considering all these things, there is many independent chemical reactions are occurring simultaneously in each cell, and once there are multiple reactions, they are subject to the complex set of internal control, and depending on this internal control, a cell may be able to adapt to the environmental fluctuations or a given environmental condition. It may be a temperature, it may be a pH, it may be a different carbon source. And further, as we are seeing, this bioprocess is continuing for the longer duration, that may lead to some genetic changes in the microbial population. Even there may be some sort of mutation due to environmental factor. So you just see there is a complex environmental phase, complex biological phase. So there are so many factors, and if you want to study the kinetics, we need to make certain assumptions. So next we are going to see, if you want to study the kinetics, how one should proceed. So first assumption, environment phase. What we are saying is the concentration of all components present in the media is sufficiently high, and the rate of reaction depends on the concentration of only rate limiting substrate. So we are going to consider the rate limiting substrate as S for the kinetics. Of course, occasionally we need to consider the inhibitor, because this is adversely going to affect the microbial growth. Third thing, as we have seen, the growth is regulated by the environmental parameters like pH, temperature, dissolved oxygen. So while we are considering these parameters are regulated and controlled. What does it mean? The change in these parameters do not significantly affect the microbial kinetics. So we are assuming there is no significant change in the environmental parameters. Next assumptions comes biological phase assumptions. So here we will see there are 4 different categories, starting with structured, unstructured, segregated and unsegregated. So structured, it considers the kinetics of change in the individual cell component present in the cell, such as RNA, DNA and protein. So each cell is considered as a multi-component. So when cellular representation is multi-component, it is a structured model. Unstructured model considers a single component system, assuming the kinetics of change of all component is same. In fact, that is also called balanced growth. So when cellular representations are single component, that is called unstructured model. Next comes segregated model. It says kinetics of individual cell is taken into consideration separately. So we are considering the cells as discrete and heterogeneous. So, all the cells are not in the same growth phase, and when we say it is unsegregated, the growth characteristics of individual cells are assumed to be same, or we are doing average cell approximation. So, in the case of unsegregated model, we consider average cellular property. So, in this way, based on the biological phase assumptions, we can have structured, unstructured, segregated and unsegregated model. Typically, the real condition is structured and segregated, and the most ideal for the kinetic study is assumed to be unsegregated and unstructured model. So, here we can quickly see what we have assumed in the environmental factor. We are assuming sufficiently high concentration of growth media except one rate limiting nutrient and constant environmental parameters. In case of biological, there will be two cases. One is cell to cell heterogeneity, and if it is not there, that is called average cell approximation. And second, if you are considering average cellular property, that is the balanced growth. Now, we can summarize here: unstructured, structured, unsegregated, segregated. Segregated to unsegregated, we say that is the average cell approximation. Structured to unstructured, we say it is a balanced growth approximation. So, which is the most ideal one? Ideal one is both simplified, unstructured and unsegregated, and actual case is segregated and structured one. So, here we are considering multi-component and cell to cell heterogeneity. This is the actual case. So, here what it says: structured, unstructured, segregated and unsegregated. Now, when we are going for kinetic models, we may have structured and segregated model, structured and unsegregated model, unstructured segregated models and unstructured and unsegregated models. So, in this way, this microbial growth kinetics can be classified into these four different types of models. Typically, the unstructured model assumes fixed cell composition, or we say the balanced growth, and the balanced growth assumption is valid primarily in single stage steady state continuous culture or the exponential phase of the batch culture. It does not hold good during any transient conditions. So, balanced growth approximation is valid at steady state, particularly continuous culture or exponential phase of batch culture. How fast the cell responds to the perturbation in its environment and how fast this perturbation occurs determine whether pseudo balanced growth can be assumed. For example, if cell response is fast compared to external changes, and if the magnitude of these changes is not too large, for example, let us say 10 to 20% variation from the initial condition, then still one can apply the unstructured model rather than going for the structured model. So, it says it is obvious that there will be environmental variations and it is difficult to assume this steady state condition, but still if you see the change in the variation is not too large, one can apply unstructured models. And when these perturbations are large, they cannot be described satisfactorily by unstructured models. Now, before we proceed for the monad model, let us quickly revisit the difference between enzymatic reaction and microbial fermentation process. In case of enzymatic reaction, usually globular protein with an active site catalyzes a specific reaction. In case of microbial, different type of reactions are carried out by the living cells. Each enzyme requires a specific substrate. Here a microbe can utilize a variety of substrate. This works only a particular pH and temperature, and microbes requires optimal range of pH and temperature. Here these enzymes are non-living, so enzyme does not have the characteristic of acclimatization, but cells have acclimatization property with respect to environmental condition or substrate. In fact, for this we observe the lag time. Every reaction requires a substrate, and here cells require a growth media which requires not only one substrate but carbon source, nitrogen source, vitamins and minerals. Now, why we discuss? Because for enzymatic reactions we have derived the rate using Michaelis-Menten equation, and for microbial, as we are going to discuss the monad model, we will just see the similarity between Michaelis-Menten and monad model. So, growth profile we can quickly see as we discussed in the last lecture. Specific growth rate can be written in terms of biomass or in terms of number of cells, and we have noted the 4 different phases: lag phase, growth phase, stationary phase and death phase, and these phases can be explained in terms of specific growth rate. In case of lag phase, specific growth rate is 0. In case of growth phase, we say specific growth rate is equals to the mu max. In the case of stationary phase, again we say specific growth rate is 0. In the death phase, specific growth is less than 0. So, in fact, we used to calculate mu net. Mu net will be mu max minus mu. So, this is a kind of driving force for the cell growth. So, monad equation, it was described by Jacques Monod based on some experimental observations. So, he observed the growth of E. coli in synthetic medium where glucose was rate limiting substrate at 37 degree centigrade. So, you just see these points are experimental data. And by seeing this experimental data, he observed the nature of curve is hyperbolic. So, he applied a hyperbolic equation. It says rate is directly proportional to C, and in hyperbolic equation it says rate is proportional to C divided by C1 plus C, and Rk is the constant here. If you just see this analogy of this equation is very much to the Michaelis-Menten kinetics or Langmuir adsorption isotherm. In case of Michaelis-Menten kinetics, we say V is V max S divided by Km plus S. Then Rk representing here V max, C1 representing here Michaelis-Menten constant. So, what was the maximum value observed here? The division was 1.35. In fact, you just see Rk is 1.35. So, Rk is actually correlates with the R max. So, R max is 1.35 and C1 value is, if you remember what is the Km value? Km value is the substrate concentration when V equals V max upon 2. So, here similar when its value is half, let us say this is R by 2 and corresponding value is C1 and that value is coming out to be 0.22 into 10 to the power 4 mole. So, C1 is similar to the Km and Rk is similar to the Vmax. So, this is the you can say this a good comparison between Michaelis-Menten equation and monad equation. Now, in the monad equation there are certain assumptions. The first one is one substrate limiting is the growth. So, it says microbial growth is primarily controlled by one limiting substrate, it may be glucose or any other carbon source. Now, second is growth rate is proportional to the substrate concentration. Third is we are assuming homogeneous microbial population, we are not considering the heterogeneous population. It says cell in the system are identical in behavior and no genetic variation. So, we are assuming average cell approximation here. Further, we are not considering any inhibition, no substrate or product inhibition in the monad equation, and steady state condition for intracellular reactions. So, these are the assumptions under which condition this monad equations explains the experimental data. Now, let us further discuss how we can derive this monad equation. So, it says for the growth, what is the driving force? It says d mu upon ds is proportional to driving force is mu max minus mu, alright, and assume this proportionality constant is following a power law function. So, we can write d mu upon ds, k is constant, mu m minus mu to the power p, where k is a system constant and p may be termed as kinetic order of the process. Now, we can rearrange this equation like d mu upon mu max upon ds equals k. We are taking mu max common here. So, this will be mu max p minus 1 minus mu upon mu max to the power p. We can further simplify by putting mu upon mu max as x. Now, this equation is simplified as dx upon ds equals k mu m to the power p minus 1 minus x to the power p. Now, it is easy to integrate this equation. So, once we are going to integrate this equation, so we can write dx divided by 1 minus x power p equals k mu m p minus 1 ds. So, we can integrate this and the condition will be when s is 0, x is 0. So, after integration we are going to put x is equal to 0 at s is equal to 0, and if you simply integrate it, we will end up with this will be 1 minus x to the power 1 minus p minus 1 equals k p minus 1 mu m to the power p minus 1 into s. So, this is the relation we have got when p is not equals to 1. If I put p equals to 1, then what will end up here is, if I put p is equal to 1 here, then will end up here is ln minus ln 1 minus x equals mu, this term will be 1 because P is 1. So, this will be K into S, and if you rearrange this, so this will be mu x is mu upon mu max we will get mu equals mu max 1 minus e to the power minus ks. In fact, this is another kinetic model that is called Taysher model. So, this when the value of p is 1, we end up with Taysher model. Further, if you put p as 2, if I put here p as 2, value of p as 2 here, so we will have 1 minus x to the power minus 1 is equals k mu max into s, and if I put again x as mu upon mu max, so we will have mu upon mu max minus mu equals k mu max s, and if I try to rearrange in the form of mu, so we will end up with mu is k mu max square s upon 1 plus k mu max s, or further we can rearrange, it says mu max s upon 1, what we are dividing with, k mu max plus s. Now, this equation can be further simplified and written as mu max s divided by ks plus s. So, this term we are replacing with ks. So, in fact, it says ks is inversely proportional to 1 upon mu max. So, in this way, for p equals to 2, we got the mu equals mu max s upon ks plus s. This is the monad equation. So, monad equation, it says mu is related with the s, and this is a hyperbolic function, and this is analogous to the Michaelis-Menten equation and enzyme kinetics, where mu is specific growth rate, unit is time inverse, mu max is the maximum specific growth rate, unit time inverse, s is the concentration of a limiting substrate, milligram per liter or millimole per liter, and ks is half saturation constant or the substrate concentration at which mu equals mu max upon 2. Further going ahead, now we can quickly discuss what is mu max. Is the maximum rate at which microbial population increases in size per unit time per unit biomass. Mu 1 upon x dx upon dt, and we are talking mu max. So, we are having maximum rate. We are not assuming any substrate inhibition. If you assume the inhibition, we have to take care of that rate of inhibition part as well. And what are the factors which affect the mu max is type of microbe, media, environmental condition, temperature, pH, oxygen availability. Significance of mu max, where it will be exploited, it can give information how fast microorganisms can grow. In case of CSTR or continuous culture, it helps us to calculate the residence time, dilution rate and feed rate. It helps in determination of optimal substrate concentration and media optimization. One can identify the rate limiting step. Further, once you know this kinetic parameter, it enables us a better process control and automation, and in case of batch time, it enables to calculate batch cycle time and enhancing the productivity. Next constant is Ks, that is half saturation constant, as we have discussed, very similar to the Vmax. When mu max equals, when mu equals mu max upon 2, then S becomes equals to the Ks. This is a simple definition of half saturation constant. The substrate concentration at half of the maximum specific growth rate. In fact, this is also called half velocity constant. Now, similar to this Michaelis-Menten equation, you can have mu as mu max S Ks plus S. There can be two cases: at low substrate concentration, when S is less, this equation turn out to be mu equals mu max. So, here we are going to have two variation. In one case, mu equals mu max S upon Ks, and in other case this will be mu as mu max S upon S. When value of S is very high, in that case this will be cancelled out. So, this becomes mu equals mu max, and here it's become mu equals mu max S upon Ks. So, this is a 0 order and this is first order. So, high value of Ks means organisms require a higher substrate level for efficient growth. Low value of Ks means high substrate affinity. It means low value of substrate can lead to the maximum growth of microbes. So, as we have seen, the Ks indicates the affinity. So, it indicates the affinity towards substrate. In fact, Ks is inversely proportional to affinity of microbes towards substrate. Further, this parameter is helpful in designing the process and bioreactor when substrate limitation is concerned. It also enables to select a particular strain for a given environment. In fact, if you see the next slide, depending on the substrate, a microbe can have different Ks values, and different microorganisms are having different Ks values. So, for a given bioprocess, one need to choose which microbes according to their affinity toward the substrate, and for the given microbe or given microorganism, which limiting substrate should be explored. Now, we will see two quick examples. First, consider an activated sludge process operating for the treatment of municipal wastewater for the removal of organic pollutant using a bacterial strain. Maximum specific growth rate was found to be 0.55 hour inverse. So, mu max is given 0.55 hour inverse, and value of half saturation constant was Ks 5 gram per liter. The substrate concentration value was measured to be S equals 3.5 gram per liter. Then we have to find a specific growth rate of bacterial strain at this substrate concentration. So, we can directly use the equation is mu equals mu max S divided by Ks plus S. All the parameters are given here, and we will get the value of 0.23 hour inverse. We will have one more example here. Consider a microbial culture that follows monod equation for a specific growth rate, and values are as follows: mu max 1.5 hour inverse, Ks 3.5 milligram per liter. It says at which value of substrate specific growth reaches to 67% of its maximum value. So, it says mu upon mu max equals 0.67. So, we can rearrange this equation. This will be mu upon mu max equals S divided by Ks plus S, and from here we can get the value of S as mu upon mu max into Ks divided by 1 minus mu upon mu max. So, all the parameters are given here. We will get the value of S. So, at this value the specific growth will be 60%. In fact, if you remember what we have discussed, if you increase the S and mu, it increases and reaches to the plateau. So, at very high substrate concentration, it directly reaches to mu equals mu max. So, I will stop here.